Hello, my friends. Welcome to the second episode of The Outrageous Making of. So, what makes a man exactly? Is it kindness? Poetry? Genius? As toxic masculinity would have it, a man is defined by his strength, horizontally, vertically, obliquely. Heck, even outlets as tame as NPR bemoan the state of the American man. Most recently, as indicated by our declining grip strength. But grip strength may not be as random as it first appears. Scientists say it's a good index of many things: lean body mass, carpal tunnel syndrome, juvenile arthritis, even Olympic potential in powerlifting. I say it's a good index of just how far I can push my 3D printer. But enough jibber jabber, it's Tomo time! Today I'll be showing you how I made a grip strength analyzer using not electronics, not circuits, but 100% plain old 3D printed plastic. So grip strength testing is as old as time. In the olden days there was hand-to-hand combat. In the 70s it was card deck tearing. And nowadays we have fancy measurement devices known as hand dynamometers. The point of a hand dynamometer is to show how many kilos of force you can exert by squeezing. And, until now, if you wanted a good one, you'd have to pay. A Jamar will run you $225. So as the study cited by NPR showed, the number of kilos that can be squeezed by the average young male has plummeted as we've moved from the farm combine to the TikTok. My partner Alexandria kindly crunched the numbers on this and found that male numbers declined. Female numbers declined. European numbers plateaued. The question for me was, what kind of mechanism do I use to replicate the functionality of these hand dynamometers? Do I imitate the geniuses like Henry Segerman and make a branched scissor mechanism? Maybe bust out a torsion spring? Or a variable rate spring with various sections? But I was too lazy for that, so I decided to just use a regular spring. It was time to start brainstorming. Thankfully, there were a bunch of constraints to make this phase easier. I didn't want to rely on support material. It's too much work to remove. And I sure as heck didn't want to do any assembly or touch-up work. The plan was to divvy up the mechanism into modules, which I could refine and troubleshoot in isolation. It's like my band director, Mr. Scavone, used to do. Workshop the hard bits in rehearsal, and only play the full chart a day before the big show. So I focused on the positioning of the handles in a rack and pinion gear to indicate the exact number of kilos being squeezed, and a 5-second timer, and finally the biggest challenge of all, the springs. Now, I could train a pet monkey with a hangover to print a normal one, but making a spring that's not fragile and not flimsy is hard. Crazy hard. I ended up having to create a program that could do it automatically. It adds a cap and a base and lists out all the parameters on the base. Which meant it was time for brake testing. I was 9 painstaking versions in, and still a long way from something usable. It was time to get serious. I printed a deflection measurement device and a mandrel to keep this thing well behaved. I baked the springs in the oven,
made them fatter,
increased the pitch, changed the layer height, the infill density, the outer layers, the print speed and temperature.
Went to my local strength measurement facility. And at 3:13 p.m. on February 27th, I put spring test 67 into the device and it was the magic recipe. Sometimes I could automate testing in software to save time and money. But most of the time, there was no substitute for flesh and blood, trial and error. That meant failures. Lots of them. There's graveyards in my bedroom, and graveyards in my CAD, Every module has its own plot and epitaph. But in 3D printing, there's no such thing as accidents, just happy disasters. Which I learned stuff from. After 3 weeks, it came time to combine all my modules into a single package, a fully functional grip strength analyzer. The thing worked perfectly, well, in theory, but the design looked like it had been laid by a rabid rooster. It needed a full makeover. But how to inject beauty, tectonic rigor, into my analyzer? Vintage Japanese electronics? German mechanical calculators? Collector pistols? In the end, I settled on making all the thicknesses, the empty spaces, the fillets, multiples of 3 millimeters. 2/17 of an inch. The legs are extruded arcs that I sliced at a pleasing angle, and, well, that's it. After a 4-day-long print, here it is, a complete grip strength analyzer. 8 springs, each with my magic recipe, provide the resistance. The grips, while lean, are strong, comfortable, and track cleanly. The needle, with the help of a little math and a rack and pinion gear, shows exactly how many kilos of force are being applied. Thanks to Alexandria's number crunching, I show percentiles here, so you know just how you stack up. Whatever. User testing indicates it is fun to use. What do you think?
Does it work?
I'm reasonably happy with the result. It's accurate, costs just $24 in plastic, and in CAD at least, the printed version is a bit coarse. It has some sex appeal. But TBH, I would have liked to have added so much more. How cool would it be to add collapsible origami mandrels, allowing me to reduce the part height? Or a tension adjustment knob to keep this thing accurate for years? And a 5-second timer, the industry standard for grip strength test duration, would have made a nice addition. But I can't be spoiling y'all just yet. While I'm afraid the grip analyzer doesn't say anything about my manhood, it does go to show that giving your 3D printer a workout can give you real gains. Anyway, if you'd like to hear more about any part of this outrageous project, check out the links in the description and comment below. There's a lot more where this came from, so do subscribe. Thanks for tuning in. I'll see you next time.